Imagine you're standing on a bridge at midnight and someone hands you an apple and says, "Drop it." You do. It falls. Of course it falls. Everything falls. You've known this since before you could talk. But here's the strange part. Nobody, not one single human being who has ever lived, actually knows why. That sentence sounds wrong, doesn't it? We have rockets on Mars. We have satellites orbiting the Earth right now, beaming this very video to your phone. Surely we understand gravity by now. And yet, if you corner the smartest physicist alive and ask them, "But what is gravity actually?" they will eventually shrug and say something like, "We don't really know. We just know how it behaves." That's the secret nobody tells you in school. Science doesn't always answer why. Most of the time, it only answers how. And gravity is the biggest example of that gap in all of physics. So let's go back, not to Einstein, not even to Newton. Let's go back to a man lying under a tree doing absolutely nothing important on an ordinary afternoon in 1666. Isaac Newton was 23 years old. Cambridge University had shut down because the plague was tearing through England, killing thousands. So Newton, like a bored student sent home during a pandemic, went back to his mother's farmhouse in Woolsthorpe. He had nothing to do. No lectures, no deadlines, just time. And there's a story, maybe exaggerated, maybe not, that he was sitting in the garden when an apple fell from a tree. Now here's the thing people get wrong. Newton wasn't shocked that the apple fell. Everyone knew apples fell. What shocked him was a different question entirely. Why does the apple always fall straight down toward the center of the earth and never sideways or upward? And then his mind did something remarkable. He looked up at the moon in the daytime sky hanging there and thought, what if the moon is falling too? Stop and sit with that for a second, because it's one of the most beautiful ideas in the history of human thought. The moon isn't sitting still up there. It's not glued to the sky. It's not held up by some invisible shelf. Newton's insight was that the moon is constantly falling toward the earth, just like the apple, but it's also moving sideways so fast that as it falls, the curve of its fall matches the curve of the earth's surface curving away beneath it. It falls and falls and falls forever. And because it's going fast enough sideways, it never actually hits the ground. It just keeps missing. That's what an orbit is, not stillness, not magic suspension. It's a perpetual, graceful falling that never lands. So Newton did the math, and he came up with something that felt almost like a magic formula. Every object with mass pulls on every other object with mass. The bigger the masses, the stronger the pull. The farther apart they are, the weaker the pull. He wrote it as an equation, and it worked. Predicted the orbits of planets. It predicted tides. It predicted comets returning on schedule decades before they arrived. Newton's law of gravity became one of the most successful ideas in the history of science. But here's where it gets interesting, and where most textbooks quietly go silent. Newton himself was deeply uncomfortable with his own theory. He wrote in a letter that the idea of one object pulling on another across empty space with nothing in between, no rope, no rod, no contact at all, was, in his own words, so great an absurdity that he didn't believe any thinking person could accept it. Ride that again. The man who discovered the law of gravity thought his own law was absurd. He knew how gravity behaved. He had the equation. He could predict exactly how hard the Earth pulls on the moon and how hard the sun pulls on the Earth. But he had absolutely no idea what gravity actually was, or how it managed to reach across millions of empty kilometers of nothing to grab hold of something. Newton gave humanity the how. He never touched the why. And for over 200 years, nobody else did either. Then came a man working in a patent office in Switzerland, stamping paperwork for inventions. Definitely not the kind of job you'd expect from someone about to rewrite the universe. Albert Einstein wasn't satisfied with objects pull on each other through empty space. It bothered him the same way it bothered Newton. So he asked a question so simple that it sounds almost childish. What if gravity isn't a pull at all? Here's the thought experiment that changed everything. And Einstein himself described it as the happiest thought of his life. Imagine a man falls off the roof of a building. Terrifying, obviously, for the man. But here's the strange detail Einstein noticed. While he's falling, before he hits the ground, that man feels weightless. He doesn't feel the pull of gravity at all. His body and everything around him, his phone, his keys, anything falling with him, falls at exactly the same rate. There's no force pressing on him. He simply floats midair in free fall. Einstein realized something enormous hiding in that simple observation. Gravity and acceleration's the same thing. You cannot tell the difference from the inside between standing still on Earth and being accelerated through empty space at the right speed. Your body can't distinguish. Gravity is pulling me down from the floor is pushing up into me. From that single insight, Einstein built an entirely new picture of the universe. Forget invisible strings pulling planets around. Instead, picture space and time as one single flexible fabric. Physicists call it space-time. Now imagine placing something heavy on that fabric like a bowling ball dropped onto a stretched-out trampoline. The fabric doesn't stay flat. It bends. It curves downward around the heavy object. Now roll a marble across that trampoline. It doesn't roll in a straight line anymore. It curves because the surface itself is curved. It looks from the outside exactly as if the bowling ball is pulling the marble toward it, but nothing is pulling anything. The marble is simply following the shape of the space it's moving through. That is gravity, according to Einstein, not a force reaching out and grabbing you. Not an invisible rope, it's geometry. The sun bends the fabric of space and time around itself, and the Earth isn't being yanked toward the sun. It's simply following the straightest possible path it can, through space that has been curved by the sun's presence. We call that curved path in orbit, but really, the Earth thinks it's going in a straight line. It's space itself that's bent. This idea is called general relativity, and Einstein published it in 1915. And here's the part that should genuinely give you chills. It wasn't just a nice metaphor. It made predictions, real, checkable, terrifying predictions. Einstein calculated that if his theory was true, then massive objects like the sun should bend light itself, not just marbles or planets, but actual beams of light passing near it. Nobody could test this on a normal day because the sun is far too bright, and any starlight passing near it gets completely washed out. But on May 29, 1919, something rare happened, a total solar eclipse. For a few minutes, the moon would block the sun completely, and stars near the sun's position would become visible in the darkened sky. A British astronomer named Arthur Eddington organized 2 expeditions, one to a remote island off the coast of Africa, another to Brazil, just to photograph that eclipse. They needed to see if the positions of stars near the sun had shifted exactly as Einstein predicted, because the sun's gravity had bent their light on its way to Earth. The photographs came back. The stars had shifted exactly by the amount Einstein calculated, not Newton's amount. Einstein's amount overnight. A patent clerk from Switzerland became the most famous scientist on the planet. Newspapers ran headlines like "Revolution in Science" and "Newton's Ideas Overthrown." A quiet man who once couldn't get a university teaching job had just proven that space itself bends, that gravity isn't a pull, and that the entire universe operates on a kind of geometry too strange for the human eye to see directly, but real enough to bend starlight across millions of miles. So now you know 2 very different stories about the same falling apple. Newton says mass attracts mass across empty space with an invisible force. Einstein says mass bends the space around it, and things simply follow the curves. Both of them, strangely, give you the right answer for almost everything you'll ever need, for building bridges, launching rockets, landing on the moon. NASA still uses Newton's simpler equations for most spaceflight calculations because they're accurate enough and far easier to compute, but only Einstein's version correctly predicts the bending of starlight, the slowing of time near massive objects, and the existence of black holes, regions where space-time curves so violently that not even light can escape the well. And yet, even Einstein's beautiful geometric picture isn't the final answer, because gravity still refuses to fully cooperate with the rest of physics. Every other force we know, electromagnetism, the strong nuclear force, the weak nuclear force, all obey the strange rules of quantum mechanics, the physics of the very small, where particles behave like probability clouds and nothing is quite certain until you measure it. But gravity doesn't fit into that picture. Not yet. Nobody has managed to write down a theory that successfully merges Einstein's curved space-time with the twitchy probabilistic world of quantum particles. Physicists call this unsolved puzzle the search for a theory of quantum gravity, and it remains one of the biggest open questions in all of science. So here's where we land. Hundreds of years after that, Apple supposedly fell in Woolsthorpe. We can predict gravity with extraordinary life-or-death precision. GPS satellites orbiting above your head right now have to correct for Einstein's time warping effects, or your phone's map would drift off by miles within a single day. We can detect gravitational waves, ripples in space-time itself, caused by 2 black holes colliding over 1 billion light-years away, using instruments sensitive enough to notice a distance change 1,000 times smaller than a single proton. We can send a spacecraft to Pluto 4 billion miles away and have it fly by within seconds of the predicted time. We can do all of that. And yet if you ask the honest question, the one Newton whispered in a letter, the one that still isn't fully settled, what is gravity actually at the deepest level? Why does mass curve space at all? What is space even made of that it can curve? The honest answer today is still in part we don't fully know. Maybe that sounds unsatisfying. But think about what it actually means. It means the apple that fell centuries ago, the one everyone assumed was simple and boring, turned out to hide one of the deepest mysteries in the entire universe. It cracked open a story that runs from a bored student under a plague lockdown, to a patent clerk daydreaming about falling elevators, to astronomers chasing a shadow across the ocean during an eclipse, All the way to scientists today listening for ripples in the fabric of reality itself, and it's still not finished. Somewhere out there right now, a physicist just as unsatisfied as Newton and Einstein were is staring at a blackboard or a laptop screen trying to find the next piece of this story. Maybe they'll be the one to finally answer the question that's been sitting quietly under every falling apple since the beginning of time. What is gravity really? We're still falling toward the answer.